Hello everyone, my name is Xu Xiaohui. I'm going to talk about the topic of infinite series. Uh, I will introduce two subtopics and use the questions as a clue to each of them. The first subtopic is the sequence. Here is a definition of a sequence. A sequence is a function whose domain is a set of positive integers, which can be presented as the form NFM. Here's an illustration. Now that we know what a sequence is, it's natural to think about what Fn will look like as n goes to infinity. And that brings us to the idea of limits. Yeah, we use the epsilon n language to describe the limits of a sequence, like this, like the definition 16.1.2. And we have also many other definitions like convergent or divergent. We say if the limit if the sequence A sub n has a limit, then we say A sub n is convergent. If the limit does not exist, we said the sequence is divergent. Here's illustration. We can use the definition to determine the limit of the sequence is 0. So the definition is directly, but it's complicated, I think. So if the formula of the sequence is simple, maybe we can use the definition. But what if the expression of the sequence become more complicated? How do we know the limits? So we have to find some more principle to help us to determine whether the sequence have a limit. Here we have definition 60.2.1 and many other definition. The increasing for a sequence or decreasing, and the lower bound and the upper bound, and if a sequence have lower bound and also have upper bound, then we say the sequence is bounded. And we have the theorem 16.2.7. A bounded Metonic sequence is convergent. So now we have this theorem to help us to determine whether a sequence is convergent or divergent. Then we can come to the second question, how to calculate the limit. Theorem 16.1.4 tells us we can use the method we calculated the limit of the function fx to help us to calculate the limit of the sequence Fn is the same. And we have also we also have many principles to help us to calculate the limit of a sequence, just like the theorem 16.1.5. For example, we can calculate the limit of this sequence. Here we use the theorem. We use the theorem here, and we use the L'Hopital's rule in the last step. In the last step, here in the last step, we applied L'Hopital's rule, which is to take the derivative of the numerator and the how to say denominator, and then take the limit, right? We know the limit is 1/2. Then we go to the subtopic 2, infinite series. Why we have to introduce the subtopic 1? Because we use the sequence to help us to define to define it the infinite series. So for the definition here, we may ask, what does the summation of an infinite series really mean? We know what it means to add finite terms, but what does it mean? But what does it means to add infinite terms? Does it really have sense? Have any? Does it make sense to add the infinite terms here? So let's check it out. We noted the infinite series like this, and we noted the partial sums as S sub n here. We say if the partial sums S sub n has a limit, then we say the infinite series is convergent, and we say the sum of the infinite series is S. If the partial sums does not have a limit, then we say the infinite series is divergent, and it does not have a sum. Example 2 here. Consider the infinite series here. It's a simple example. We can calculate the partial sum like this. It's easy, right? The partial sum is n over n plus 1. So the limit is just 1 here. which means the infinite series is convergent, and the sum is one here. This uh, this is another example. The partial sum is it's a sum. This is a sum. This is a sum of the first terms of geometric series. Geometric series, right? So the partial sum is 2 minus is like this. Then we can calculate the limit. The limit is 2. So we say the infinite series here is convergent, and the sum is 2. The example 2 and example 3 is simple, I think. And we can directly calculate the sum of the infinite series because it's simple, right? But what if the expression of the infinite series is become complicated? How can we calculate the sum, or even whether there is a sum, which means how to determine the convergence of the infinite series? Here we have some theorem here. Theorem 16.3.3. If the infinite series is convergent, then the limit of the terms is equal to 0. This condition is necessary but not sufficient, which means if the limit of the term is not equal to 0, then the infinite series is divergent. But if the term have a limit of 0, we still can't make sure that the infinite series is convergent because the condition is not sufficient, right? So we need more new accurate conditions to help us to determine whether the infinite series is convergent or divergent. So here's the theorem 16.3.9 and 16.3.10. And here is a comparison test. In this theorem, we can use another infinite series, maybe a more easier infinite series, or something we know. We already know about the convergence, right? To help us. So the conclusion is if U sub n is less than V sub n, then the infinite series composed by V sub n, if we know the infinite series composed by V sub n is convergent, then we definitely know that the infinite series composed by U sub n is convergent, right? Because you just think the big one is convergent, then the smaller one is convergent too. It's easy to understand, right? The theorem 16.4.3 is limit comparison test. This is very important. We can use limit forms to help us to understand. For example, here's example 4. Determine whether the infinite series like this is convergent or divergent. We can use another infinite series to help us to determine this series, right? So we use Vm. We use this. This is a geometric series, right? And we use the limit comparison test here. We know that the conclusion is right. The first condition, right? So from the first condition, we know then both converge or both diverge, right? But from example 3, we know that the geometric series is convergent. So we know here, the example 4, the infinite series in example 4 is convergent too. Right. There are many other theorems and tricks that we can use to see if a sequence converges or not. But since time limit, we only show 2 most important conclusions. Here we go. This is very important. P-series. The conclusion is if P is greater than 1, then the P-series is convergent. And if P is less than or equal to 1, then the P-series is divergent. If we use P-series and together with the limit comparison test, we can determine the convergence of infinite series more easily. For example 5, I determine whether the infinite series here is convergent or divergent. We can use P-series, V sub n, P-series, right? Then we use the limit comparison test here. We know the limit is 1, right? Since the P series here, the P is 2 over 3, is less than 1, right? So the P series is divergent. So according to the limit comparison test, we know that the infinite series here in example 5 is divergent too. Then here we come to the question 3. What are the applications of series? If an infinite series is convergent, it means this infinite series is equal to a real number S, right? Then we may think we can extend it. We can extend un to unx. Then we can extend the number S to a function Sx, right? Of course, if we go to Sx, we may we have to know the domain of X, right? Here's a definition. 16.7.1, a power series in X subtract A is a series of the form like Formula 1. If X is a particular number, then the power series 1 becomes an infinite series of constant terms, like we concerned before, right? If A equals to 0, the power series becomes a power series in X, which we say is a Maclaurin series. If it is convergent in a certain extent, then we say the power series in X defines a function. If A equals to 0, right? Then fx equals to the formula 2. When the expression of Cn is different, we say the formula 2 here. If the Cn is different, the convergence of the power series 2 is also different, right? There are many theorems and tricks to determine the convergent field of the fx. Here, example 6. So we can determine the interval of convergence of the power series here. Right? We only need the ratio test, applying the ratio test here. We know the given series will be absolutely convergent if the abstract of x subtract 2 less than 1. According to the Maclaurin's formula, we have some very typical power series here. And we know the interval field where the convergent, right? And with this formula power series of the power series, we can apply the power series to approximate calculations here. This is an application. This is a typical application of the series in engineering aspects. For example, here we know the power series, the formula of the Ex here. Then we substitute the -1 into the x. Then we have the result here. It's not too difficult, right? We can calculate the result is like this. So here's an example for us to see how we can apply the immunity series to help us to calculate some numbers, right? This is all my presentation. Thank you very much.